welcome back. My name is Greg Dick. I'm the Executive Director of Advancement and Senior Director of Public Engagement here at Perimeter Institute. In the spirit of respect and reconciliation, we acknowledge that Perimeter Institute is located upon the lands that have been inhabited by Indigenous peoples from the beginning. In particular, we acknowledge that it is situated on the traditional territory of the Anishinaabe, the Ottawandaran, the Haudenosaunee, and the Neutral peoples. Perimeter is located on the Haldimand Tract. After the American Revolution, the tract was granted by the British to the Six Nations of the Grand River and the Mississaugas of the Credit First Nation as compensation for their role in the war and for the loss of their traditional lands in upstate New York. Of the 950,000 acres granted to the Haudenosaunee, less than 5% remained Six Nations land, and only 6,100 acres remain Mississaugas of the Credit land. We thank the Anishinaabe, the Ottawandaran, the Haudenosaunee, and the Neutral peoples for hosting us on their land. It is great to be back, and we are excited to share another online public lecture from our socially distant studio, now set up here in the empty Mike Lazaridis Theater of Ideas here at Perimeter Institute. As you watch the talk, I encourage you to join the conversation online. We are at Perimeter on Twitter if you want to chat with the Perimeter scientists or if you want to ask a question of tonight's guest speaker. Tonight, we are joined by a researcher whose research has taken her from the balmy temperatures of the Bahamas to the cold remoteness of the South Pole. Professor Naoko Kurahashi Neilson is a member of the IceCube Neutrino Observatory collaboration, an experiment searching for high-energy neutrinos deep down in the dark glacial ice of Antarctica. She is currently an associate professor at Drexel University and the recipient of the National Science Foundation Career Award, and was featured in the Get to Know 10 Early Career Experimentalists by Symmetry magazine. After her undergraduate degree from the University of California, Berkeley, she obtained her PhD at Stanford University while listening for extremely high-energy neutrinos in the ocean in the Bahamas. Her postdoctoral research took her to the University of Wisconsin, where she continued her research as part of the IceCube collaboration. Tonight, she will explore how neutrinos are providing new insights into our universe and what it's like to be neutrino hunting in Antarctica. Dr. Kurahashi Neilson, welcome. How are you today?
Thank you. I'm well. Thank you, Greg.
So, and where are you coming to us from?
I am just outside Philadelphia here.
Oh, very good. Well, thank you so much. We are so delighted that you were able to have you with us today to give your talk. Maybe I'll just hand it over and take it away.
Absolutely. Thank you for the invitation. So here I am at the geographic South Pole. So that is not the magnetic South Pole. The magnetic South Pole is where your compass points south. This is the geographic South Pole. So that pole marker here, if I can use my arrow here, cursor here, that pole is the pole in which the Earth rotates around. So I got a globe here. So if you spin the globe, that where the stick intersects with the Earth, that is that pole right there. And a fun fact I like to share about being at the geographic South Pole is if you stand there, no matter which way you face, you can keep turning yourself around. No matter which way you face is north. So yes, it turns out mapping something that it's a 3D surface onto a 2D flat map is very hard. Okay, so today I would like to tell you why I'm at the South Pole first, and then I'd like to tell you what we learned from the South Pole. So let me start with the first one. So this is my favorite thought experiment. So pretend you're an alien scientist, and your field of study is the human hand. And pretend you don't have human hands. The only human hand accessible to you is wherever you're sitting on the other side of the room. So there's a human hand on the other side of the room, and you have to stay where you are. You can't go up there, touch it, dissect it. You want to study the human hand from the other side of the room. What would you do? So if you're a good alien scientist, what you would do is look at it in different ways. So maybe optically, using human eyes, you know that, at least in my case, my hand looks pinkish, yellowish, whitish. But if you used X-ray vision, if you took an X-ray image, you would know that my hand has bones inside. If you took an MRI image, you would understand that I have muscles inside. And if you put on your infrared night goggles, you would know that my hand is warm, it emits heat. So in short of going to somewhere and studying it by physically having access to it, the best way to study something is by looking at it in different ways. So this is what the exact analogy is for astronomy here. So this is the Crab Nebula. It is a star with a lot of gas around it. And we know that because we've studied it in different eyes. So here is the exact same location on the sky seen in radio image, ultraviolet image, optical, and X-ray. And you can see that even though it's pointing at exactly the same place in the sky, you pick up different features of the Crab Nebula. So by studying the stars and the galaxies using different visions, you understand more about what's there. And what we want to do is to see the universe in neutrinos. So what are neutrinos? So neutrino is an elementary particle. And what is an elementary particle? So everything you can see or touch, the air, your computer screen, me, you, air, desk, everything is made up of molecules. And molecules are made up of atoms. And atoms are made up of the nucleus and the electron. And as far as we know, the electron is not made up of anything. We can smash the electron with high energy as much as we want. It does not break apart into other things that it is made up of. So an electron is an elementary particle. The nucleon is not. So the nucleus has nucleons, which are neutrons and protons, and they are made up of quarks. And as far as we know, the quarks are fundamental particles. They are not made up of anything else. So a neutrino is an elementary particle or a fundamental particle. It is not made up of anything else. However, it is not part of what makes me, you, air, desk, the world we live in. It is a particle that comes out in nuclear reactions. So the nuclear reactors, they emit neutrinos. And the sun also emits neutrinos because the sun has a fission process, and the nuclear reactors have fusion. So, I'm sorry, that's the other way around. Nuclear reactors have fission and the sun has fusion. So all these nuclear processes create neutrinos. And in fact, we create neutrinos too. We have some potassium in our body, and very, very occasionally that potassium will decay. It's a nuclear decay, and will emit, in this case, antineutrinos from our bodies. So we're a neutrino source, even though it doesn't make up the things we touch and feel and use every day. They're also known as the invisible or ghost particles, and that's because they rarely interact. So they are not electromagnetically charged. That means they don't bend when there's a magnetic field. So they travel in a straight line and they hardly interact. And that is what we want to use to study the universe. So why? So if you want to look at the high energy universe, and we're talking about things like supermassive black holes or active galactic nuclei, so these are galaxies with so much energy and stuff, one of the most violent things in the universe, right? We want to look at these high energy phenomena. You have three messengers, three signals you can choose from. One is cosmic rays. So cosmic rays are charged nuclei, and you can see in this cartoon here, it's depicted in red, and this is electrically charged, so that bends in the magnetic field. It turns out space has several magnetic fields, so even if we do observe these cosmic rays, if you point back from Earth, you're misaligned and you can't see where it's coming from. So cosmic rays have their problems in studying the universe. Well, what about light? Most of astronomy, absolutely everything, almost everything we know from astronomy was because we've been studying the stars using light for centuries. So at these energies, the photon, the light, is gamma rays. And gamma rays are great because light is electromagnetically neutral. They're not charged, so they point straight back and they're not affected by the magnetic fields in space. However, if I have a flashlight and I try to shine it through a book, you know that the light won't come out of the other side of the book. So photons interact. That's why it gets trapped. So if you imagine a gamma ray being emitted by these supermassive black holes, they may not come to you because there's some dust in between you and the supermassive black hole, or oftentimes, wherever these gamma rays are created within this supermassive black hole or active galactic nuclei, excuse me, it could be obscured because there's usually these very energetic places have a lot of stuff. So maybe you don't get all the signal in light. And then comes neutrinos. So neutrinos are neutral, so they travel in a straight line. We can point back to where they came from. And again, they don't interact much. They're the ghost particles, so they travel in a straight line without being obscured. So if I had a neutrino flashlight and I had a book, the neutrinos would go straight through and you would see it on the other side. And that's what we want to do. Okay, so let's do another thought experiment. Have you ever been buried in snow? What if you're buried a mile deep or a kilometer deep? What do you think it looks like? Should you see light? No, it actually gets very dark in there very quickly. So if you bury yourself in, and I don't recommend this, but if you bury yourself in a mile of snow, it would be pitch black, except once in a while, very high energy particles will whip across and emit light, and that's called Cherenkov radiation. And these particles that whip across fast, they need to be charged. So Cherenkov radiation only happens for particles that are charged. And that's what we did. We are looking for charged particles made by the neutrino at the South Pole. So the experiment I work on is called IceCube, and I'll explain why. So here it is the surface of the South Pole. So remember the first picture where I'm standing right next to the geographic South Pole. I am actually on top of 2.8 kilometers of glacier ice. That's about 1.8 miles. So this is really high altitude. I actually got altitude sickness at the South Pole because it's being on top of a tall mountain, essentially. So there's a lot of glacier ice at the South Pole. And we have dug down deep into the ice, 2.8 kilometers deep. And we have buried light sensors, over 5,000 light sensors in a volume of a kilometer by kilometer by kilometer of ice. And that's why it's called IceCube. So I just threw out that kilometer by kilometer by kilometer, very nonchalant. But for those of you who run, or for those of you who understand distances, think about wherever you are and a kilometer away, right? That's quite large. Now think about doing that in the other direction and then going up that kilometer too. That is how big our neutrino detector is. And it has to be because we're looking for very rare events. So these light sensors, they all have cabling with signals that come up to the IceCube lab, or ICL. So this is a modern 2-story building. It houses all our computers and all the cables that come from deep underneath the ice. They go into this computing warehouse and we process the data there. So this is an artist's view of what that might look like. And you see the blue Cherenkov light depicted there. Okay, so now let's see a real event, real data that IceCube has seen. So here you see the strings. I don't know if you can make out, but every little, once in a while, there's a dot, and those are the light sensors. And here's that particle coming in. It's blue light. That's the Cherenkov radiation. And then the colored blobs, those are the light sensors and how much light it saw. So the bigger the blob, the more light it saw. Let's try that again. And then they're color-coded. So yellow is early. I think red, yellow, green, blue is how it goes in time. That blue light we added on later. It's not something we can visualize like this. All we get is that dots, right? That data. And the red line is our reconstruction. That's our best guess, throwing lots of computational resources, best guess at which direction this neutrino came from. I'm going to play that one more time. Because I want to point out one more thing. See how the neutrino is sneaky. It doesn't emit any light until it interacts with the ice there. Bang, interaction. Then there's a charged particle, in this case it's a muon, that it created. And that's what the trail of light is that we see. So there's nothing coming in because before it interacts, it's a neutrino, so it doesn't emit light. Okay, So this is a huge scale collaboration. We have over 200 scientists. I believe there's 11 countries now, with many, many institutions involved. And this is a great international project. You become tight-knit with many people around the world, and it is fantastic to work in such a community. So I said, next I'll tell you what we learned from the South Pole. But before I jump onto the second part, I'm going to do a little show and tell to space them apart. So let me talk to you about my journey to the South Pole. So if you think about a map, a world map, Antarctica is like this long white thing at the bottom of the map. But of course, again, it's a projection issue, right? That's not really what Antarctica looks like. So again, if you take that globe and look at it upside down, this is what this looks like. So here's the outline of the continent of Antarctica, because it is a continent, and that's the South Pole. So first, when you go to Antarctica through the United States Science Program, you fly to Christchurch, New Zealand, which is here in the southern island of New Zealand. And then you exit your normal passenger terminal, and then the next building over is this United States Antarctic Program passenger terminal, or USAP terminal. And this is your gateway to Antarctica. Christchurch, New Zealand is also where you get all your gear. So if you showed up in tank top and flip-flops, they will give you jackets, really nice jackets, Canada Goose jackets, long underwear, socks, boots, everything. So first, let me show you sort of the international map of the stations at the South Pole. And my first trip was to McMurdo Base, which is in coastal Antarctica. So this is me arriving in McMurdo Base. This is my first time being on the continent of Antarctica, so I look quite happy. That's the plane that took us there. It has wheels. It lands on ice, so the ice serves as runway. And because you need nice, smooth ice to land, it's usually a little bit far away from the station. So there's these funny buses to take you to the station. And McMurdo Station is very interesting. There's a lot of biology. Penguins are there. It's cold, but not, the time I went, which was austral summer, not unimaginably cold or anything like that. And then from there, I fly to the South Pole. And so the plane gets noticeably smaller. Also, I don't know if you can tell, maybe in the next slide, this plane takes off on wheels and lands on skis, because in the South Pole, there's a skiway, not a runway. Here are the pilots flying this. This is mid-flight. They're reading a book. And it's just white and flat out there. So South Pole is a plateau. It's just, again, as I said, it's 2.8 kilometers high, but it's a plateau. So it's just white, flat, and there's no geographical markers to tell you where you are. So I was taking a peek out of the plane's window, small little window, and I thought we were still cruising altitude. And all of a sudden, the plane shook, and I realized we landed, because it looks exactly the same from the window, whether you're about to land or you're high up. It's just blue skies, white horizon. So these pilots are amazing. So here it is, the plane on skis, and here I am at South Pole Station. And that is like nothing I have ever experienced before. It is desolate, it is flat, it is high altitude, as I said before. There's no living things there, not even like microbes or germs, unless we've brought it in with us. And here's me being happy at the South Pole.
Oh. I'm gonna run around the world. Okay. And that's how it's done.
Right. So I think if you're from Canada or somewhere cold, you can hear that crunch, crunch sound of the snow. You know it's cold when the snow crunches like that. So that's me being happy at the South Pole. I visited in the austral summer, but it turns out in the winter there, the station closes, and that's because it gets too cold for planes to take off or land. So what happens is we leave a handful of people, maybe 30 or 40 people behind at the station to what's known as winter over. And they will not be able to leave the station for the next 6 months or so. So up until now, these were all my pictures, but this is a picture I got from a winter over a couple years back. So this is the winter overs at South Pole Station waving bye to the last plane of the season. And they won't see another new plane come in for another 6 months or so. And then what does the sun do? So in the winter at the South Pole, it's night, right? It's 6 months of darkness, 6 months of daylight. So in between, there is sunset that takes weeks. So I just want to tell you here is the summertime picture, and this is a time-lapse composite picture of the sun. So the sun at the South Pole just circles around the sky every day, circles, circles, circles. And gradually it gets lower and lower and lower, and then you have a couple of weeks of sunset. So the sun is setting very gradually every day as it spins around every day. And then winter comes and nighttime comes, and these stars and these auroras come out. So that's the IceCube lab, where we house our computers once again, and beautiful sky. I mean, the winter overs sent very nice pictures. You almost want to go there for 6 months just to see the aurora, but not really. I don't think it's worth it for me. Not quite. My sanity. There's the auroras and my sanity. Okay, so that was the intermission. So now, what did we learn there? That's what I want to tell you about next, the second half of the talk. So I told you we wanted to study the universe and neutrinos. We wanted to see what it's like out there if we put on our neutrino glasses. I think everybody would have, or at least most everybody would have agreed that these supermassive black holes, these interesting, super energetic, super violent things out there in the universe make neutrinos. I think everybody would have agreed to that, but we hadn't seen anything. We hadn't seen any neutrinos come from outside our galaxy. Until 2013 when IceCube saw them. So let me tell you about this story. So this is an energy line. What I've done here is the further right you go, the higher energy it is. And in particle physics, we use units of EV, electron volts. And this is the energy an electron gains after you cross 1 volt. But and to make it a little bit more, or not, intuitive, I've converted it to the amount of energy dynamite explosion equivalent. So here we are. The highest energy particle humankind has ever seen is in the form of cosmic rays. And remember, these are charged nuclei, so these are in the charged particles category. And they go up beyond 10 to the 20 eV. So that's like tens of milligrams of dynamite exploding. That much energy in one particle that your eyes can't even see. So these are extremely high energy particles. We know how to accelerate charged particles. This is what we do at the LHC. So they accelerate protons and smash it against each other. But the highest energy we can accelerate on Earth by human-made technology is about here, right? Between 10 to the 13 and 14 eV. And gamma rays goes higher. We've seen gamma rays a little bit higher than those energies. But in 2013, what happened was IceCube saw the highest energy neutral particle ever observed at the time. So this was about here. And this made the cover of PRL. So that's an event, and it looks different from the previous event I showed you, where it's a nice line you can point back, and that's because there are different types of neutrinos and different types of interactions, which I won't get into in this talk. So why is high energy interesting? Why do I keep hammering home about high energy? So here's a plot. So I'll start with the upper left. And the x-axis is neutrino energy, and this is a log-log plot, but if that means nothing to you, don't worry about it. So this covers many, many orders of magnitude of neutrino energy. So the more right you go, the higher the energy. And y-axis is the flux. So that's how many neutrinos we see, right? And it's how many per this big of a bucket, per amount of time that you put the bucket up to catch these neutrinos. So it has funny units, but at the end of the day, it's some normalized amount of counts of neutrinos. And as you can see, as you go higher in energy, you expect less and less neutrinos. So they're more rare, right? So let me zoom into this part of this huge energy spectrum, because this is where IceCube pretty much operates. So I'm blown up here, right? And so both of these plots show different components of the neutrino spectrum, what causes them. And it turns out, so green here or blue here, there's a lot of neutrinos created in the Earth's atmosphere. And those are our backgrounds. We are not, for this purpose, for what I'm talking about, in fact, IceCube studies these neutrinos in pretty good detail, but for our purposes of trying to see these supermassive black holes and other things far out there outside our galaxy, these are background events, and we don't want them. What we want is the orange here, labeled astrophysical, or pink here, labeled neutrinos from AGNs, again, active galactic nuclei, violent galaxies. And so as you go higher in energy, you see that the astrophysical neutrinos, these neutrinos from our sources that we care about, takes over. So the higher the energy they are, the more likely they are to be from outer space, to be from outside our galaxy, and not created in the Earth's atmosphere. Then the same year, we saw a handful of these neutrinos, and this was at the point where we said, okay, there's just no way, statistically speaking, some, if not all of these neutrinos have to be from outside our galaxy. So we created a buzz. We made the cover of Science that November in 2013, and we did a lot of press. So if you search for 2013 IceCube, you can probably read a lot of articles from back then. This is my favorite headline of all of them. Extraterrestrials on Earth. Scientists find outer space stuff at the South Pole. So I think describing neutrinos as astrophysical neutrinos as outer space stuff is just perfect. And then I thought, oh, maybe it's a tribute to The Thing. So for those of you who don't know, The Thing is the 80s film. Oh my gosh, it's a long time ago now, a 1982 film about scientists being trapped at a remote Antarctic base where they can't get out, and aliens keep killing them. So, okay, so we've found these neutrinos. It turns out, yes, things beyond our galaxy emit these very high energy neutrinos, and we've found them. But the question is, where do they come from? What makes these extremely high energy neutrinos so high in energy we can't even think about making on Earth? So this kind of is related to the question, how do you know with your own eyes that there's a star or a galaxy when you look up at the night sky, right? So let's say I know that there must be a star or a galaxy right here. And I know this because when I look at the night sky, there are more photons, more light particles hitting my eyeball from just here compared to the surrounding. And that's how I know that there's a star there. Right. So if you think about the particle physics, implication of how your eye works to look at the stars, it's amazing. This, whatever it is, it's very far away. It has created lots of photons, and a good chunk of them traveled all the way to your eyeball and hit your eyeball just for you, so you can know that there's a star there, right? So it's very romantic if you think about particle physics in that way. But basically, we want to do the same thing. So we want to map all the neutrinos we have. This is a projection onto the sky. So if you think about it, if you imagine yourself at the middle of the Earth, the equator here is the sky looking up, scanning across the equator, sort of, and going up is from the middle of the Earth, looking to the North Pole and through and beyond. And of course, south this way. So this is a projection. Again, we're talking about projections of 3D spaces in 2D, but this is one way to project the sky. And this is very old. This is old data from back in 2008 when we didn't even have the whole detector completed. And the reason why I still use this is because if I gave you the newest and greatest dots, it'll just be black. You can't really tell them apart. So here's all our neutrinos reconstructed to where they came from, and do you see a cluster, right? And that's how you look for sources of neutrinos. We do it a little bit more sophisticated. We have complicated statistical likelihoods that we do use to look at the sky. And so we convert it to this type of hotspot searching map. And so the circles here are the hottest spots in the north and the southern hemisphere. In the sky. So we've been doing this exercise for a long time. And up until 2018, we never saw anything that was statistically significant. We never saw a hotspot. So even though in 2013, we proved that there are things out there that emit very high energy neutrinos, we didn't know where it came from. And then in 2018, first hint of what makes these neutrinos came. So again, this is the cover of Science, and again, this is an artist's view of what it's like down there in the IceCube detector with these light sensors. So each of these is a light sensor. And of course, the answer is right here, neutrinos from a blazar. So what happened in 2018? So in that Science magazine, in the Science publication, we have two articles there. So I'll walk you through both of them and what we found. So the story goes back to September 22, 2017. A huge event happened in our detector. So we know for various reasons that this was a neutrino-induced muon, so a charged particle created by a neutrino. And the neutrino itself was so energetic that the muon it created went through the whole detector and splattered all this light that filled our detector. So again, reminder that this is a kilometer across. So think about one subatomic particle your eye can't even see emitting light continuously for more than a kilometer. So this is a lot of energy. So we traced that back. We, again, threw all our computers into figuring out where in the sky it came from. So we try to trace this back, right, as well as we can. And it came from around the arm of Orion, the constellation Orion. So it's right here. And it turns out, and so we can't pinpoint exactly. Of course, there's always going to be error. So we say, oh, we think this neutrino came from here plus minus this error circle. And within that error circle was this blazar. Now, a blazar this is TXS 0506. This is AGN, an active galactic nuclei with a jet coming out, and that jet is facing us. So these jets are just spews relativistic particles, and it beams. And when the beam is facing us towards Earth, that becomes a blazar. So every time we see these very high energy neutrinos, we send out alerts. And we've been doing that for a couple of years now, and that's nothing that interesting. And the fact that there was a blazar within our error circle, that's also, I mean, that's significant, but it wasn't alone. It wasn't as interesting as intriguing, but nothing was conclusive from that. But when we see these very high energy events, we send out an alert to our friends, our telescope friends. So they did what's known as a follow-up observation. So these are all telescopes that use the electromagnetic light, essentially. These are light telescopes of different energies, and some are space-based and some are ground-based, but all of these telescopes heard from us that we saw something. We saw a very high energy neutrino from that direction, plus minus this error circle. It contains a blazar in it, and they looked at the blazar, and what they found was that the blazar in light, in gamma rays, was flaring. So flaring means that there's this nominal brightness of blazar, and at this point in time, it was emitting much more than it normally does. So now we have this not only in space, but in time coincidence of a flaring blazar with a high energy neutrino, and that is very rare. So we did a promo video about this, so I'll show you that. The other thing you should know is that was the first Science article. I said there were 2 Science articles in that magazine, in that issue. The second result, as this video will explain, is that once we knew where to look, once we knew that, oh, this blazar might be interesting, we went back to our archival data and looked at the neutrinos that came from there. And we saw that there was a neutrino flare, not a gamma ray flare, not a photon flare, but a neutrino flare a couple of years previous to this 2017 observation. So I'll run you this video. So here are all these high energy alerts we did throughout the years, and there's like one a month. So that's not interesting. But then there was the September 2017 alert, which happened to coincide with this TXS 0506 blazar. And now we go back to 2014, 2015, and all of a sudden we noticed that there were so many events, so many neutrino events clustered in that location. So there seemed to have been a flare of neutrinos a couple of years prior. So that was the second result. That was the second publication. And here it is. This is the timeline of that neutrino flare. So this is the year, and you can understand the y-axis as how much neutrinos above background we saw from this particular spot in the sky. And you can see that towards the end of 2014 and to the beginning of 2015, there's a huge flare here. Okay, so we did another round of press. So again, if you Google 2018 IceCube, you'll see a lot of interviews. I'm in a lot of them too. And unfortunately, there were no like treasured headlines like before, or not that I picked up. If you find anything, let me know. But since then, we have seen more sources of neutrinos. So possibly. So remember that that map where we scan for hotspots. And I said before 2018, we didn't see anything in particular exciting. So it turns out lately we've been seeing a hotspot emerge, and it's a galaxy called NGC 1068, and it may be emitting neutrinos. What's interesting here is NGC 1068 is not like the blazar we found in 2018. So the blazar, this is not a blazar. This is an AGN, but it has no jet. It is much closer. The blazar was very far away. It's, let's see, 6 billion light years away. This is like 50 million light years, so it's much closer. It's a much more benign galaxy. That there's no relativistic jet spewing at us. So there's not much in common, and I think that's an interesting mystery. So where do we stand? We've discovered neutrinos from outside our galaxy. I think that's settled. We've seen it. We know it is there. Everybody thought it was there, and we saw it. We're starting to see the first couple of sources that make these neutrinos, but we only have seen known sources. So both the AGNs that I talked about that have names, we already knew it was there because of light observation, photon observations, right? So we've only seen things that we already know are there, and that's because it's just easier to look for things that we already know where they are. But if you go back to the motivation slide of what neutrino astronomy could be and why we want to use these, it's very possible that there are sources out there in neutrinos that we don't know about, we haven't seen at all in the light spectrum, right? So we haven't seen any unknowns yet, but I think that'll be really interesting to see if any of those pops up. And then what does the neutrino sky look like? What makes these sources unique? As I said, there's not a lot of things in common between the two sources we may be seeing neutrinos from. So what's the underlying connection here? What makes some blazars? Because we know there's a lot more blazars, and heaven knows we've looked at all of them, and we don't see neutrinos other than that one, at least not for now. So what makes some of the sources more special than others? And what does that tell about our universe? Once we have a sky view, a full sky view of what the universe looks like in neutrinos, what does that tell us? I think those are good questions that we are yet to answer, that we're starting to answer right now. So I will leave it at there.
Thank you so much, Dr. Kurahashi. That was terrific. That was a lot of fun. All right, and we already have questions flowing in, so I'm just going to jump right to them. So the first question, the IceCube Neutrino Observatory seems to be one of many recent collaborations of hundreds of people spanning many countries. What are the benefits and challenges of such massive undertakings?
Yeah, that's a great question. So I think the benefits is, I mean, there's scientific benefits. You get to pull your resources together. There are people of different backgrounds who think differently, and so it's much more stimulating and engaging, and you come up with good ideas. Definitely, there are non-scientific benefits too. I mean, you name a country, I might know somebody from there, right? So the world becomes a smaller place for you, which I think is fantastic. The drawbacks is, so we very much prioritize meeting each other face to face, which has been very hard for the last couple of years. But also when we do, you have to get to know each other. And even though we have this whole network of how to collaborate online efficiently and have ways to do science together remotely, it works so much better once you know each other face to face first. So that's hard. That's hard because you have to get to know each other, and then the remote collaboration works better. So that was already hard, and then I think it's been very challenging these last 2 years. That's a great question.
Yeah, no doubt the challenges are real. We'll get there. We're going to get past this. Another question, just digging into the physics a little bit. If neutrinos decay faster than the time it takes them to reach a land-based instrument, how does that work?
So the neutrinos don't decay. The neutrinos are the products of the decay. So the nuclei decay. In the case of the potassium that you have in your body decaying, that's the isotope that's decaying. And as so this is in particular, this is beta decay. So as it decays, it produces, in beta decay's case, an electron and an antineutrino. So in the case of what happens in these stars and galaxies, it's definitely a nuclear process that happens. It's a high energy process that breaks nuclei, and that's what causes these neutrinos. Certainly we have to think about it at not in terms of stable matter like what we have around here, but more like a plasma or something like that, where there are components of particles floating around, right? Non-elementary particles in the jet. So that's how the neutrinos get created in a very hand-wavy sense. And then they travel to us, and once you create a neutrino, they don't, again, they're the ghost particles, so they don't interact. So they come to us unobscured. Now the problem is we want to detect them, right? So we need them to interact at our detector or close to the vicinity of our detector. And that's why our detector is so huge, because neutrinos hardly ever interact. So we got to find those rare things and catch them.
How many interactions are there in a day, an hour, a month? I don't know.
So we record, and they're not all neutrino-induced interactions. Many particle interactions happen at our detector, and we have to take it offline and figure that out. But online, real-time, we record at 3 kilohertz, about 3 kilohertz. So 3,000 events a second. And we're on 24/7, like 365. The detector is on all the time. We want to get as much data as possible since we built that thing. And even now, as I speak to you, in the 1 second I took right there, there was 3,000 particle interactions that were recorded at the South Pole.
Wow, that's incredible. Well, let's stick on that too, because I remember we were chatting the other day, and you said that I was surprised at the locality of how accurate you could point in the sky. Can you talk a little bit more about that? That was really interesting.
Yeah, so the angular resolution is the term we use to say, so I was talking about the error circle in the sky. So the name of the game is to make that as fine as possible, right? The less error you have, the more you can pinpoint, the more sure you are which source gave out those neutrinos. So this is something we spent quite a bit of time on, computing resources on, and we, even after 10 years of creating this detector, we still continue to make progress on. And I think this is a hard problem. So there's a couple of things that go into making this hard. One is that our detector is not man-made. It is the ice that we were given, right? So we did not make the cubic kilometer of ice. It was just there as a natural thing. So we don't know too much about the properties of ice. And when a charged particle goes through and does this Cherenkov radiation where it emits light, the light doesn't travel straight to our light sensors. A lot of times the ice scatters the light. So we need to understand that scattering of light, every single photon in our detector, and that contributes to a lot of error on the angular resolution. The other thing is this is an energy dependent problem. So the higher energy the event, the more light we have to work with, the better we can sort of nail down the error circle. When you only get half as much or a tenth as much light, then you tend to have, it depends on the topology, but you tend to have a bigger opening. So it gets harder as you go lower in energy.
Oh, thank you. That's good. More online questions. Yesterday was World Teachers Day. What role did teachers play in your chosen path?
Oh, this is such a great question. I certainly had great teachers and mentors, and I'm lucky to have those. And I had interesting ones too, which I think makes the journey fun. The role the teachers and mentors had for me, I think is that because I wasn't like a kid or a student who won all these like, most likely to succeed kind of awards. I think them believing in me was a big motivator and a big confidence builder, actually, to stay on this path. So if it weren't for teachers, not everybody, but the handful of teachers who really believed in my abilities to do this, I don't think I'd be here. So I think that was important. And also they had fun. They had fun talking about science. They had fun talking about math. And you want to do what's fun. So I think making it look fun is fantastic, especially if you're a student and you're still young, quite young. I think that's what's attractive about this.
This sort of plays right into that answer. So why did you choose to do science outreach, like delivering a talk just like this one? What motivates you to do that?
Right. So many reasons. So when I was a kid, I used to love watching like NASA launches and things like that. And I always thought the interesting part was, the science was interesting, but also like everybody getting super excited and hugging each other in the control room. I thought that was kind of interesting too. So it's like, social dynamic wise, because it's not like these people won the lottery. It's not like they're going to get rich, right? They do it because they love it. And they're so happy that it worked. And it's this team who had this common mission that had nothing to do with, fortune, that personal wealth that wanted to do this. And so, sorry, I kind of deviated to what made me want to do this. So I think seeing that was very motivating to me, to know that you can spend your life on something that's bigger than you was motivating to me. And I think it's nice to think about things that's bigger than you once in a while. And so having, being able to provide that opportunity is really my honor. It's been an honor and privilege for me. And also, not a lot of people look like me. When I saw science programs on TV, a stereotypical physicist would be Einstein, right? So it's a crazy mad scientist. I think I'm quite normal. So I think it's a good opportunity to show people that, you can be a normal person and still be a physicist. That's what I try to do. I don't know if I succeed, but that's what I try to do.
Oh, absolutely succeed. Oh, that's great. Well, let's wrap up with the speed round of questions, which is always so fun to do. Are you ready? So single answer, phrase, whatever comes to mind. No wrong answers. Okay. Here we go. Where's the next exotic place you'd like to conduct research?
Ooh, somewhere warm, definitely not cold anymore. Hawaii would be great.
Fantastic, no wrong answers. Very good. Favorite particle other than a neutrino?
Oh, that is a good question. Oh, that is a very good question. I am gonna go with, whatever I say, I'm gonna get made fun of by my colleagues. I'm gonna go with the photon. I'll just do the obvious thing. The photon, obviously, gives us light.
Love it. One scientist, dead or alive, you'd most want to meet?
Maria Goupert-Mayer. So I've read this book of famous female scientists that my PhD advisor gave me. And most of the early female scientists' lives were quite tragic. But it looks like she had a fun life. So it would be her.
Fantastic. Future scientific development you're most excited to see?
I would like to know what it looks like in neutrinos. Like beyond these two possible sources, I want to know what makes these super energetic neutrinos out in the universe.
All right.
And I hope it happens before my career is over.
You already got the follow-up. The follow-up was when do you expect to see it? So perfect, before the end of the career. Love it. Okay, two more. Biggest influence on your career, scientific or otherwise?
I think I'd say my mother. She was not a scientist or anything like that, but I think at every point she asked me if what I was doing contributed to war, and that's a really interesting question coming from a non-scientist, and I think it's good to ask yourself that once in a while.
Oh, love it. And if you weren't a physicist, what would you be?
A volcanologist.
Ooh, volcanoes. Oh, Dr. Kurahashi Neilson, thank you so much. This was such a treat. Really appreciate you taking the time to spend it with us. and have a really lovely evening.
Thank you so much.
And now let's need a couple of announcements before we say goodbye to the online audience. So first of all, on November 3rd, just scrolling here to get to where I can see the date, November 3rd, we'll have our next lecture, and I can actually even let you know who it is and get you looking forward to it. So on November 3rd, we are hosting Dr. Manuel Calderon de la Braca Sanchez, and he will discuss research, his research at CERN, and the inspiration for an IMAX film, of which Perimeter was a part, called Secrets of the Universe. So we're really looking forward to that. That'll be in the first Wednesday of November. And until then, see you soon. Thanks very much. Good night.